So now this video discusses about the cross product of the two vectors. So mind you, we have two operations of the multiplication of the two vectors. We have what you call the dot product of the vectors, and that much it ended up giving us the scalar value. And we also have what you call cross product of the two vectors, and that we should have to discuss as the main point of interest in this video. So what is the cross product of the two vectors? So now the cross product of the two vectors gives us a vector as a result. Hence the cross product of the two vectors is also said to be actually a vector product. So it is also said to be a vector product because in this case of the cross product of the vectors, what we can have is actually a vector as well as a result. So what is the cross product of the two vectors? Let's say we have a vector A with the components, let's say A1 and let's say A2 and also A3. And we have, let's say, another vector, let's say, given as B1 and let's say B2 and also let's say given as B3. Now the cross product of the two vectors is symbolized as A cross B. Now what does it mean if we should have to go for the actually a cross product of the two vectors? Now what should have, we should have what you call I, J as well as K components, and that has to be presented in a specific manner, and we should have the determinant of these actual vectors. So we should have this. Now for the first vector, which is vector A, and this is its actually I component, and we have its J component, and this is actually a K component. That is Z, of course, we'll have that. And for the vector B, we'll have B1, we'll have B2, and we'll have B3. We'll have that. And then from there, we'll have to come up with the components, and for actually this actually a determinant. Then we'll have, in the sense that we'll have that law in this column. So when I have, now in that case we'll have it as, let me just have to create some space here. So now what it means is this, that we have cancelled the column for J, so which means whatever we have here will belongs to, actually we have cancelled the column for I, so which means what we have here belongs to I. So that will be given as, that will be given as, now we'll have it as I component. And what are the remainings? We have A2 and B2, A3 and B3. We'll have that. Then minus, then which means we'll have to cancel this one as well. So which means we have cancelled I, and what actually we have cancelled J, and whatever we are having belongs to that J. So which means we'll have should be J. By the way, this negative is for the formula, it has to be there. And we'll have the determinant, that is now A1, B1, and A3, B3. We'll have that. And we'll have a plus, now we'll have a K, so which means we should have to mask this one out. So whatever it is remaining is for K, and that will be given as, of course we'll have it as, that is A1, and we'll have B2 should be B1, and also that is A2 down b2. Let me have it here properly. So in this case, we'll have it as a plus. Now have for k. So have it as, now for k we'll have a1 and down b1, and I'll have a2 and down b2. We'll have that, and also we have to cross it in that way, of course. But anyway, that is how it has to be. Then what will go up next? So from there, what it means is that we'll have this times this minus this times that, and this times this minus this times that, and for all determinants. So which means we'll have now it as, for j, that is for I, will have a2 times b3 minus b2 times a3. Mind you, it has to be a uniform. So for j, we'll have it as a1 times b3 minus, b1 times a3. We'll have that. And also for k, that is a plus. For k, we'll have it as, a1 times b2 and minus b1 times a2. So that is how we should have to understand about the cross product of the two vectors. Now let's say we have two vectors. Let's say we have vector a, and which is given as, let's say 2, 1, let's say 2. We have, let's say, vector b that is being given as, let's say -5, 0, let's say 5. Now what is the cross product of these two vectors if that is the case? Now principle remains the same. We'll have I, j, and also k. And for the first vector, we have 2, 1, 2. And the -5, 0, 5. We'll have that. And then we'll have, for I, that will be given as, now have 0, 1, should be 1, 0. Should be 1, 0. We'll have 2 down 5. That is in the minus. Should be I. That is for j. And that will be given as now 2, -5, and a 2, 5. And the plus k will have it as 2, -5, 1, 0. Then from there we'll have to express it as, now a vector I that will be given as 1 times 5, that is 5. So have 5, and the minus 0 times 2, we'll have it as 0, and the minus j, that is 2 times 5, that is 10, and the minus -5 times 2, that is given as -10, and the negative will have plus 10 here, and the plus, vector k, that is, I should say, a component k, that is 2 times 0, we have 0, and the -5 times 1, -5, and the minus, another minus, we have it as +5. We can have it as that. And for this case, we'll have it as, 5i, and minus 20j, and plus 5k. So this is what we have as, what we call it as, the cross product of the two vectors. Now how about if we have this case? Let's say we have a vector m, and that is being given as, let's say, a 5, 2, let's say 2. And we have a vector n that is given as, let's say, -2, 4, let's say 2. So now what is the dot product, actually say cross product of the two vectors in that case? So now principle remains the same. and such that we have I, j as well as the k here. That is, I'll have 5, 2, 2, let's say negative 2, 4, we'll have 2. And that is to say we'll have it as I component, we'll have 2, 4, and a 2, 2. And the minus j component, you'll have it as 5, negative 2, 2, 2. And a plus k component, that will be given as 5, negative 2, 2, we have 4 here. And what is that? We'll have a component I, that is 2 times 2, we have 4. And our 4 minus 2 times 8, 4, we have it as minus 8. And the minus j, that is 2 times 5, we have it as 10. And the 2 times 2, negative 4. In the negative, we have plus 4. And the plus, k component, that is a 5 times 4, we have it as 20. The minus, and the 2 times negative 2, we have it as negative 4. And the plus, in the another negative, we have it as a plus 4. Now, what would be that? You can see that we have it as, you can see that we have it as, we have it as negative 4i and minus 14j and plus 24, k. So this is what we call the cross product of the two vectors. So let's now go into what we call the orthogonal theory of the cross product of the two vectors. So what is the orthogonal theory of cross product of the two vectors? Let's say we have a vector A, and that is given as A1, A2, and A3. And we have, let's say, vector B, that is given as, we should have it as B1, we should have B2, and also B3. Now, what is the orthogonal theory of the cross product of the two vectors? Now, in this case, you should have to understand that the cross product of these two vectors and should give us also another vector. And let me call it as a vector C. So which means having the cross product of the two vectors, what it means is that having the cross product of the two vectors, what do we obtain? It is also a vector. So, but let me call that vector as, let's say, a vector C. So according to the theory of orthogonal of the cross product of the two vectors, it states that if we have the cross product of the two vectors, what we obtain as a vector is perpendicular to the two vectors in action. So which means the dot product which means the cross product of these two vectors gives us this vector C. So this vector C is perpendicular to these two vectors in action. That is what you call the orthogonal theory of the cross product of the two vectors. Now let's see this. Looking at this recent example, you should have to understand that what we have obtained here, it is the, let's say this is a vector C. I'll call it as a vector C. Negative 4j, actually you should have it as I, minus 14j, and a plus 4 should be k. Now, determine if a vector C is orthogonal to vector M and also to vector N. So what is that one? According to the principle behind the orthogonal vectors. Now, if two vectors are orthogonal, it means, vector M dot vector C should be equal to 0. And even vector N dot vector C should be equal to 0. So which means if this is the case, it means the two vectors are orthogonal. If that would be okay. So actually try to verify if that one will be in that way. And also let's have the following vectors. Let's say we have a vector O that is given as 2i minus 5j and plus let's say 2k, and we have, let's say, a vector B that is given as negative I negative 2j plus let's say 6k. So find the cross product of these two vectors and determine if the vector if the vector obtained will be orthogonal to these two vectors. And also try this one as well. Let's say if we have a vector S that is given as 5i minus 2j, and let's say we have a vector B that is given as, let's say, negative j. So find the cross product of these two vectors and determine if the vector obtained will be orthogonal to these two vectors, and appreciate how it will be. How about if I have this case? Let's say if we have I should have it as a vector W. Let's say it is given as 2n I and plus let's say 6, should have 6j minus let's say 4n k, should have that. Let's say we have a vector V that is been given as, let's say, should have it as, let's say, a 6, should be 6n minus, let's say, minus 5, that is I, plus let's say 7j, and minus let's say 2n k. Now find the values of, actually find the value of n. Now let me have it this way as well. We should include, let's say, we should include another parameter. I should have to, let me have, I should also have, let's say, 7mj, and here I should have, let's say, 2nm. That should be that. Should have 2nm, k is that way. Yeah, it should be that. So find the values of m as well as the n for these two vectors. So try to have that out using the principle that we have discussed recently.